Um, so I work on the intersection of neuroscience and machine learning. Specifically, I study language. I study how is language represented in our brain, and how can we actually represent language in general in any computational system, not just the brain. So before I start, I can give you an example that will motivate a little bit the complexity of the problem of language if you haven't thought of it before. So this is one of the kind of recent tests for seeing if our algorithm are able to understand language. You can think of it as like a Turing test. So it's called a Winograd Schema Challenge, and basically it's made of these sentences like this one: the large ball crashed through the table because it was made of styrofoam, and the task is to say what was made of styrofoam. So if you were to read this, what you most probably would answer is that the table is made of styrofoam. However, if you were to read this other sentence, which is the same, except that it ends with, sorry, I'm going to say it again, the large ball crashed right through the table because it was made of iron. So now you know that the thing that was made of iron is not the table, it's actually the ball. And so in order to solve this, so much is required. You have to understand, first of all, the sentence. You have to understand all the words. You have to understand what the words mean in the specific case. You have to understand, like basically grammatically and semantically the sentence. But then you also have to rely on your real-world knowledge of tables, balls, and iron and styrofoam, etc. You have to combine all these things together. And so now this task is one of the tasks that after you train a natural language processing algorithm, you can train an NLP algorithm in order to solve this. And based on your classification accuracy, you can say something about whether or not you solved this task. Now, the whole challenge here is that based on the data set you acquire, based on how much data you have, you might be able to solve this task by relying on sometimes you do solve this test by relying on some surface statistic. And what I'm trying to say is that we do not have algorithms right now. We have algorithms that do a very good job in kind of learning a lot of statistics about the data, but we haven't really solved the problem in the sense that the algorithm doesn't really understand the profoundness or the depth of a statement in order to be able to naturally solve problems like these, even though you could still get a reasonable classification accuracy on these tasks by using some kind of surface level information. So once you realize the complexity of the language problem, you can think of, if you're interested in this problem in general, of like, how does language work? How does intelligence in general works? You can study these things from multiple aspects. You can study them basically in multiple computational systems. And truly, the only computational system we know of that understands language is the human brain. And this is one of the things I'm interested in studying. So these kind of questions fall under the umbrella of cognitive neuroscience. So some of these questions are things like, how does the brain understand individual words, and how does it combine them together to create something that is above the meaning of the individual words, which is what I call here supra-word meaning. Just a simple example, when we say she finished the apple, if you understand each one of those individual words, it's not enough to understand what this is saying. This is saying that this person finished eating an apple. The word eating is something you bring just from your knowledge of language and your knowledge and your common sense. So this supra-word meaning is brought upon by basically your ability to understand a language. It's the same kind of common sense you use to solve the Winograd Schema Challenge. So the question that you might be interested in a neuroscience kind of realm is like, how is the brain doing this? Which regions in the brain in the first place are actually doing or representing this high-level meaning, the supra-word meaning, versus representing the meaning of the individual word, if we're thinking of the brain as kind of like this processing system with different parts working together. So in order to answer questions like these, I use different neuroimaging tools that record the brain activity in time. So here, this is an example of us using fMRI to record brain activity while someone is reading a text. This is a natural text. It's actually a chapter from Harry Potter, and the words are presented one at a time to the subject. And every 2 seconds, this fMRI machine, which is on campus, but we have not been able to use it in a long time because of COVID, but hopefully at some point in the future we'll be able to use it again. But so when we use it, we just kind of have a snapshot of brain activity, one snapshot every 2 seconds, and the brain activity. This is just a kind of a representation of it here. You can think of red as high and blue as low, and it's changing through time. This is one way of recording brain activity. It's slow, as I said, it's one image every 2 seconds, but it actually gives you very good spatial resolution. Other methods give you high temporal resolution and sorry, this was high spatial resolution. So other methods give you a low spatial resolution, but high temporal resolution. So they're much faster. They can give you like what is going on inside a word, like every 1 millisecond, what is the activity in the brain, but they do have other drawbacks. But the main issue here is that if you remember my questions that I'm interested in, which are like, how does the brain understand meaning? It's unclear how to solve, like this is an extremely complex naturalistic experiment where the person is just reading so many different words, thinking about so many different concepts. It's unclear how you can use this data that we are recording in order to answer these questions. And so this is where machine learning comes in. The great thing in machine learning is that we have methods that allow us to represent the meaning of language. It allows us to, we have word embedding, for example, that can represent the meaning of individual words. We have now contextualized word embeddings that represent not only the meaning of that word, but the meaning of the word context that came before it or around it. And so we can use these methods, or we can even improve upon these methods in order to represent this information. And once we have that representation of the meaning, we can use different machine learning algorithms and different statistical tools to make inferences about what is going on in different regions. And this is a difficult problem. It's very challenging. You're using machine learning to make scientific conclusions. And there's so many things involved and so many different parts of the puzzle that needs to be fixed. It takes a long time usually. And there's so many problems, starting even from like the amount of data you have, the dimensionality of the data, how do you process it, how much is too much, and like how do you make sure you're not kind of double dipping, like you know, like using the same data to make kind of decisions. I mean, there's so many levels of decision making. You should never use the data that you test your generalization on to make those decisions. But it's actually the implications of this are somewhat, sometimes it's very trivial. Okay, you should never use your test data to train, that's clear. But the implications of this are actually sometimes very subtle, and you have to always constantly question your approach as a machine learning researcher when you're trying to actually use machine learning in the real world. And specifically here, I mean in science. But in general, of course, it's always like machine learning has many things to worry about if you're using it for example, for decision making or for other aspects of the real world. So how do we use now these two components in order to study the brain? What we do is we do something we call alignment. So we take, for example, a neural network, and we take the representations of that neural network and we align them with the brain activity. And we find regions that align or that correlate through time, in which the representation in those regions correlate with the representation in the network. And depending on what level of the network we took or what information we think is in that network, we can say something about the information in the brain. And so in that way, we can kind of draw these maps that represent here, since I don't have a lot of time, I cannot tell you too much about the details, but I can tell you just high level idea. We're able to kind of disentangle the meaning that's related to kind of composing the word together and differentiate that from the meaning that's just about the individual isolated words. So for example, she finished the apple, like all of these are individual words, but if you think about the kind of super word meaning of eating, we find that actually that meaning is kind of predictive of these specific regions, and we can say something about those regions in a neuroscientific context. Now, this is a great direction, like using machine learning to inform cognitive neuroscience. But as a machine learning person, one thing that motivates me too by looking at the brain is to see if the brain can give us some intuition or some inductive bias of like, how do we actually build smart, intelligent machines that can understand language? So the idea is that can we actually use what we know about the brain or our brain data to inform the design of our algorithms? And so this is it's kind of one of the work that we did recently is we were trying to see if basically using making our representations more aligned with the brain, so more similar to what the brain is doing, will make them actually understand language better. And we have this kind of proof of concept experiment in which, so this was a paper we published last year in which we looked at transformer models for, so transformer language models that were based on transformers. And we were trying to understand, it's okay if you don't know what these are exactly, but we're just trying to understand the role of attention in these networks. And we realized that if actually we remove attention from these networks, from the early layers, we were able to improve our performance in predicting the brain activity. So in other ways, we found a modification to the network that makes this network more aligned with the brain. And once we did this modification to the network, and again, there was like no intuition why that would be true. Like we were actually like harming the network in some sense or removing something from it. And once we did that, we actually found that if you do this at the low level layers, at the early layers, you actually get improvement on many tasks that don't require retraining this network. And so that was very counterintuitive, but it was kind of like a proof of concept that actually if you make something more like the brain, it will actually perform better on a natural language tasks. And actually the interesting thing is like very recently another group found that through a completely different method found that actually it is true that these early layers don't actually even do this kind of attention. What they're doing is actually just doing some sort of averaging, which is similar to what we were doing. Okay, I quickly ran out of time. I just want to mention two more ideas. One of them is that one of the things that other ways to connect our work in our lab to the real world is through applications also in the area of medicine or brain-computer interfaces, where we can use these kind of statistical models of the brain, but actually develop them for different individuals and study their differences between individuals. And the idea here is that if we might be able to actually use these rich maps of the brain to predict specific psychiatric or neurological traits that a patient might have. And another one is that, well, something that I haven't started yet, but this is something I would be excited to start with a new student, is to kind of build a new brain-computer interface that's not invasive, but it's actually designed to work in a very naturalistic setting. This is an incredibly hard problem because typically these things are developed in a very, very controlled environment where you have to decide between a specific small number of stimuli. This will actually require kind of maybe having multiple sensors of what the subject is seeing, what the subject is listening to, and incorporating all of these into a rich model of what is going on in the subject's brain. All right, that's it. This is a picture of our lab. We were having a socially distant outing, as you can see. These are many of us, my students are over here. Actually, I'd also included the caption that was generated automatically when I put this picture in PowerPoint. It's actually funny. It's like, I guess it's an okay performance. We were not playing Frisbee. I think if you think of a human seeing this picture would never say that people are being Frisbee, but for this algorithm, which was trained probably on one of those data sets like Coco, which has a lot of people standing in the grass. Like whenever they're standing at that distance between them, they're probably just playing Frisbee. So that's probably why like maybe in the algorithm's representation, this image is extremely close to other people playing Frisbees. But for us as humans, when we see this, it's very distant from people playing Frisbee. So this is just something to keep in mind as you think of why would you even like contrast the brain and machines in case you need a motivation. Thank you.
Okay, if anyone has questions, please send email to Leila because we're into Ziv's time now.